Hey there, and welcome back to Linear Algebra. In this first day of 2 days in section 1.6, we're going to take a look at the very important notion of basis in a vector space. So the goals of the lecture, I want to motivate and define what I mean by a basis. I want to give several examples of bases inside of our known examples of vector spaces. And then I want to prove two theorems. A characterization of bases, well, at least for finite sets, we're going to limit our attention to that case. And then also the fact that every generating set always contains a basis. Okay, so we'll look at statements of them as we go. As in all these videos, I'm going to kind of talk fast and be very terse, so you can always stop this thing, think about it on your own speed. Okay, so to kind of motivate the definition, I've decided to state this lemma. Okay, so what does the lemma say? If you take a generating set of a vector space, so you take some set that spans V, but this is kind of a special generating set that no proper subset of it would span V. Right? So it's kind of a minimal spanning set in that sense. And the lemma is that it would always have to be linearly independent. We talked about earlier that I'm kind of interested in these minimal spanning sets, like a set that spans but is as small as possible. And this observation, this lemma, is that such a set would always be linearly independent. All right. So how to prove that, or at least sketch a proof of it? First of all, I'm going to do away with some sort of small cases. If G is the empty set or just has one element in it, so by this notation, I mean the size of G. So if G has no elements in it or one element in it, then it's linearly independent. That's something that we talked about back in section 1.5, yeah? So we can do away with those. So we may assume that G has at least two elements in it, okay? And for a contradiction, if it's not linearly independent, then it's linearly dependent. So suppose that it is. If G is linearly independent, then there exists some vector in G that's not zero, and it's a linear combination of the other vectors in G. So V is a linear combination of vectors in G. Take away this vector V. I'm going to use that set complement notation. Right? So I said it out loud. This is the other vectors in G. Yeah. Well, if V can be written as a linear combination of these other vectors, but then removing V from G won't change the span, right? So the span of G take away V is going to be the same thing as the span of G, right? But that was equal to V. But G take away V is a proper subset. Let me give you my notation for that. That's G take away V. This is proper subset notation. If you want to emphasize it, sometimes people write that. It's a subset but not equal to G, and that's a contradiction, right? Because we said that no proper subset of G was supposed to span. So there you go. That's the observation. If you have a minimal generating set, minimal in the sense that it generates, but any subset, proper subset of it won't generate, then such a subset is always linearly independent. Okay, linearly independent spanning sets are very important. They're kind of the building blocks of the vector space. So we're going to give them a name. This is the one and hence main definition of the lecture. And I'm defining this term basis. A basis for a vector space. Your author denotes bases by the Greek letter, lowercase Greek letter beta. So I'll do the same. And what is a vector space? A basis for a vector space? I think of it as having two components. A basis for a vector space is a linearly independent subset of the vector space that spans. All right, so I've just written those two things out down here separately. It's a basis if it's linearly independent. Remember what that means. I'm going to be brief here, but linearly independent means that if a linear combination of vectors in it is equal to zero, that all the coefficients have to be zero. All right, so here I'm not quantifying those things, but the VJs there are in beta. So that's what linearly independent means. And it spans. What does spanning means? It means that for every vector in the space, you can write that vector as a linear combination of vectors in this set, right? The AJs, of course, come from F. That's what it means to span. So it's a sort of linearly independent spanning set is called a basis. Let's talk about some examples. Oh, I thought I had a prompt here. Let me just make one. So we'll look at some examples. The first one is kind of just a technicality, but the empty set is a basis, right? We said that the empty set is a linear combination, or is a linearly independent set, and its span is the zero vector. So for the zero vector space, the vector space that contains only the zero vector, it has a basis, and that basis is empty. Not very interesting. How about in Fn? So in Fn, let's define, I think we have this notation already, but let me write it here. EI is the n-tuple that has all zero entries except for 1, and that 1 occurs in the ith position. Yeah. Then the set of all those things, beta equaling the set of E1, E2, and so on up to En, that's a basis for Fn. I'm going to leave these details to you, or maybe in the in-class lecture we can write some of them, but these things clearly span. Yeah, every n-tuple is a linear combination of these n-tuples, and they're linearly independent. The only way a linear combination of those n-tuples is going to be 0 is if all the coefficients are 0. So that thing's a basis for Fn. Sometimes it even gets a name. It's called the standard basis. The standard basis. So we'll see this later on in our course, but Fn has infinitely many different bases, but this one is kind of special and nice to work with. So that's why it gets this name, the standard basis. Cool. How about a third example? How about if we take beta to be the polynomials 1, x squared, and so on up to, say, some x to the n for a fixed n. Yeah, that's a basis for the polynomials with coefficients in f of degree less than or equal to n. So again, I'm just going to kind of speak out loud, but why does this set span? Well, every polynomial of degree less than or equal to n is an f linear combination of these monomials. That's what a polynomial is. So it kind of spans by definition. And why is it linearly independent? Well, if you take a polynomial linear combination of these things and get 0, all of the coefficients had to be 0. That's by definition of the 0 polynomial. So this thing is linearly independent and spans Pn by definition. Cool. Related, but I think important to mention, but we shouldn't also call it example 3. If we don't stop, we don't put a cap on how many xn's there are, or on what the highest power of x is, then we get a basis for all polynomials. Every polynomial is a linear combination of these things. There's no limit on how big the degree would be, and they're linearly independent for the same reason they are in 3. Fifth example, let's take our vector space to be the vector space of, say, m by n matrices with entries in F. Yeah, and let's define a matrix EIJ, I'm going to call it. And what is EIJ? Well, it's an m by n matrix. And it's kind of special in that it only has one non-zero entry, and that non-zero entry happens in the ith row and the jth column. So the way I'll indicate that all the other entries are 0 is I'll just draw some big zeros here. This thing is called an elementary matrix. There are n times m of them. And I think it's clear that the set of these EIJs, where I goes between 1 and m, the maximum row is m, and j can be any number between 1 and n, the number of columns. That's the basis for these matrices, M by N matrices with entries in F. Yeah. Again, every matrix is clearly a linear combination of these things, right? Because if you have an entry Aij in the ij entry, then it's just that number times the matrix Eij, sum them all up. They're linearly independent, kind of for the same reason that the standard basis and the n tuples are linearly independent. Right? In fact, this example doesn't really feel all that different to n tuples than me. It's just that instead of n numbers, we have m times n numbers, and instead of writing them all in one big row, we're writing them in m rows with n entries per row. Okay, so there's some examples for you to stop and think about. There are others. Let's keep going here. Let's look at our first theorem, a characterization of, I should probably, to be a little bit more honest, let me say a characterization of finite bases, because you could modify this proof slightly to delete that, but I'm going to be looking at the case of finite bases. So here's our hypothesis here. What do we have? We've got a vector space over F, and we've got this finite subset beta. I've already named its elements U1 to UN. Okay. And then what's a characterization? It's an if and only if statement. So this set is a basis. That's what I'm characterizing. If and only if every vector can be written uniquely, so it's an existence uniqueness theorem, as a linear combination of elements in the set beta. Okay, let's give a proof. I'll start by making the assumption that beta is a basis. I won't rename or rewrite the elements. They're U1 to UN. So what does that mean? It's linearly independent and it spans. Right, well, if it spans, then for every V in my vector space, I know that there exist scalars, say A1 to AN, such that V is a linear combination, AJ times UJ. Right, that's the definition of span. So that's the existence part of this. The existence is kind of a part of the hypothesis. So what do we have to do? We have to show they're unique. All right, so we have to show that these A's are the only way to write that V. Well, there's kind of a standard uniqueness. If V is also, say, the sum of, say, something B sub J times U sub J, where these B sub J's also come from the field F. Well, then two expressions that are equal to V are equal to each other, right? So we would have the sum of the AJ UJs being the same as the sum of the B sub J UJs. And if we subtracted, say, those B's to one side and gathered terms, we could write that as the sum of, say, AJ minus BJ times UJ, and that difference would be 0. Right? But the the UJs come from this set beta, which is linearly independent. And so we have a linear combination of those elements equaling 0, so the coefficients all have to be 0. So AJ minus B sub J is 0 for all J. That is, the A's were really the same as the B's. So that's the uniqueness part. Okay, so if beta is a basis, then every vector can be written uniquely as a linear combination of elements in beta. Nice. What about the other way? It'll even go slicker. If every element can be written uniquely as a linear combination, then the span of beta is V by hypothesis, right? Because we're saying every vector can be written uniquely as a linear combination of elements in B. Well, you can even forget about the uniqueness part. Just the fact that you can do it means they span V. Yeah, so why would they be linearly independent? Let's suppose that I have some scalars and 0 is a linear combination of these u's. Yeah, well, certainly 0 is also this linear combination. Yeah, take all the coefficients to be 0. So by uniqueness, sorry, I have a little remark here. I'm running out of room. I'm just gonna move it for now. So AJ is 0 for all j by uniqueness. And that shows beta is Li. All right, so if you have a spanning set that's linearly independent, you've got a basis. Nice, so that's the proof of our characterization of bases. So what was this remark that I was gonna make? The uniqueness up there means that every vector can be written in one and only one way as a linear combination of these u's. Yeah, it's unique. Well, that linear combination of those u's in a very natural way corresponds to an n-tuple. You just take the coefficients, keep them in the same order, and write them as an n-tuple. Yeah. So this uniqueness part is saying that in some sense, this vector space V, this is not a mathematical term, I'm going to make this more rigorous as we go, but V is just like Fn in some way. You know, every vector V can be written as a linear combination, and since you can do of these U's, and since you can do it in only one way, you can write this V in only one way, those coefficients completely determine this n-tuple and vice versa. And when you add things over here, a gathering like terms would be like adding the n-tuples. And so this is kind of our first glimpse. We'll make it more rigorous as we go, but it's our first glimpse that like this vector space V, in some sense, is just like the vector space Fn. Okay, so that's all I'm going to say about that right now. We'll make it more rigorous later. We have one more piece of work to do in this video, so let's try to get it done. Theorem 1.9, you're looking at the statement here. So it says if you have a vector space and you have a finite generating set, so a finite generating set G, then some subset of it is a basis, right? So what does that mean? That means there must be some subset of it that's linearly independent and still spans V, right? So in particular, if V is finitely generated just means it has a finitely generating set, then it has a basis. It has a finite basis. So that's kind of our punchline. This in particular part is just a rephrasing. If you're a finitely generated vector space, you've got a finite basis. Vector spaces with finite bases are going to be the principal object of study in this course. Okay, so how to prove this? I'm going to actually give a proof, a somewhat formal proof by induction. I'm going to start off by kind of saying that without loss of generality, it's one of my favorite acronyms in mathematics, without loss of generality, the zero vector does not belong to this set G. If the zero vector did belong to the set G, I would remove it. I still have a finite set and it wouldn't change the span. So that's what I mean by without loss of generality, is that I can just assume that 0 is not in this set G. Okay, so we're going to proceed by induction. The proof is by induction. On the number of elements in this set G. All right, so I'm going to kind of show you a formal way to write this induction. So I'm going to let S be a subset of the numbers 0, 1, 2, the natural numbers plus 0, if you like. Let S be a subset with the following property. So S consists of those natural numbers that are greater than or equal to 0, such that whenever G is a generating set of size S, so for all subsets G of V, the span of G is V, and G has n elements in it, then G contains a basis. Okay, so S is the set of sizes for which this theorem is true. And for example, 0 belongs to this set S. Because why? Well, if G has 0 elements in it, and the span of G is V, well, then V must be the 0 vector space, and G contains a basis. Right? The empty set is a subset of G, and it's a basis in that case. So there's our base step, if you like. If you want, I don't, this isn't necessary, but the element 1 belongs to S as well, because if G has 1 element in it, remember, without loss of generality, I'm assuming that that element is not 0. G doesn't have the 0 vector in it. So if G just has 1 element in it, well, then the span of G is just all the scalar multiples of that vector V, right? Say V is some non-zero element in G. And so we can take V as a basis. So those are just sort of the base steps. So now my induction hypothesis. Let's suppose for some n, and since I've checked it for 1, I can suppose that n is at least 1, that the numbers 0, 1, all the way up to n all belong to this set S. And what I want to show, I'm giving you lots of acronyms here, I want to show that n plus 1 belongs to S. Right? If I can show that, then the principle of mathematical induction says that S is equal to all natural numbers. And that's what I'm trying to show. I'm trying to show that that statement in the defining property for S, I want to show this statement holds for all natural numbers. Right? Cool. Okay. So how do I show that n plus 1 is an S? Well, I have to start by saying, suppose I've got some set G that spans V, and it's got n plus 1 elements in it. So let's do it. Suppose that G, say, has things in it like, I don't know, U1, U2, up to UN plus 1. It's a subset of V. The span of G is V. All right? And my goal is to show that that G contains a basis. I want to show that G contains a basis. Okay, well, if G is linearly independent, then G is a basis. And we're done. Otherwise, there's some element, there exists, say, some UI in G, with UI being an element of the span of G take away UI. Very familiar tool in our argumentation. Just for notational convenience, without loss of generality, let me assume that UI is this last one. If it's not, I would just rename things. Okay, so UN plus 1 is in the span of G. So the span of G take away UN plus 1 is still V. But the set G take away UN plus 1 has n elements in it. The size of this set, UN plus 1, is equal to n. So by our induction hypothesis, this set G take away UN plus 1 contains a basis. G take away UN plus 1 contains a basis. Well, any subset of G take away UN plus 1 is also a subset of G, so G contains a basis. Okay, so by the principle of mathematical induction, any finite set that generates V contains a basis. And that's what we wanted to prove. Okay, thanks for listening.